Test. Hello everybody. This is a Meet in the Middle live stream. Code versus sees the stream. Yep, cool. In the, I think, description on YouTube, you already have that. Yep, you do. Also Twitch chat, I'm giving you the link now. I will go through those problems. All of them require meet in the middle technique, but also obviously we need to talk about when in general to use meet in the middle. Now, this technique is more about solving problems rather than just talking about it. Well, for example, segment trees. You need to learn segment trees, then you know what they do. Here it's slightly different. You just, there are some in some ways you will figure out when to use it, when not, but then that's it. Every problem will be different from now on. From that point, I mean. Why is my stream under tag software and game development? Because it's the closest tag there is. If you have a better suggestion, then please tell me. Meet in the middle works if, or you should use it, if you can solve problem for twice smaller k or n or whatever there will be in the problem. In such cases, you should use meet in the middle. And this is then different than divide and conquer. Divide and conquer is a similar technique, and that one is about always splitting the input in half, doing recursively something for both halves, and so on. But if there is a problem and you have a sequence of length 200,000, it's not that if length was 100,000 instead it would be significantly easier. You still wouldn't know how to solve it. And here, this sentence means that if n was twice smaller or k was twice smaller, then you immediately know how to solve a problem just with some technique, and that's always related to the problem. What is that exactly? Here's, and an example will be problem 1, where we will split the input into 2, because for each part we can solve it, for each half we can solve it, and it's small enough, and then there will be some merge of that, but we don't go recursively. It's not like divide and conquer. Okay. Simplified version of the first problem is the following. So this is, let's say, P1 easy version. Given n up to 40 numbers, find subset of them, summing up to s, to the target value s. You're just given a sequence of length 40. All numbers are up to 1 billion. AI and s are up to 1 billion. This is the most basic meet in the middle problem. Why we use meet in the middle? Because this sentence applies. If n was twice smaller, I mean, this k is just anything. You can rename n into k. If n instead of 40 was up to 20, this is an easy problem. The solution is check all the submasks. So all the subsets in complexity 2 to nth power, maybe 2 to nth power times n, doesn't matter much, easy. But now, if n is twice bigger, I just say that maybe we should use meet in the middle to run the solution that works in this time complexity for both halves, and then in some way we will combine it. So let's see, and the goal will be to then achieve this time complexity. 2 at power n over 2. There are 2 halves, each with 20 elements, and for each of them I will do something. Maybe here it will be multiplied by n or by logarithm, by just something small. This is the target time complexity. We're solving easier version of this knapsack problem, or just it's exactly this one? Oh, then I thought that this is a knapsack problem where there are values and weights. It's exactly this problem, sorry. Exactly this problem. I misremembered something. It's a bit stupid that I wrote this down. Anyway, we want to get the target sum x. How do we achieve this? And we will keep getting back to this sentence, so do remember it. All right. For the left 20 elements, I can iterate over all the subsets. I will talk about, let's say, n equal to 6. There are 6 elements. The first 3 are, say, 2, 1, and 6. And then in the second half, there will be also some 3 elements. For those 3, I list down all the possible subset sums, which are 0, 1, 2, 3, 6, 7, 8, 9. Some of them can be repeated too. That would be possible, but here we have those. We have, I will call it L1, list 1, and this is of size 2 to 20th power. Then similarly, I make a list for the second half, and now I need to combine it. Let's say that my target value is 10. Then whenever I see a sum in the first half, I know what should be the corresponding sum in the second half, in L2. If I'm looking at here, I want to know if the second list, this one, corresponding to the right half, if it contains a number 8. If so, problem solved. So now we got a problem given 2 lists with 2 to 20th power elements, take one element from the first list, one from the other, so that the sum would be x. And this is easy. You can keep that in sets, or you can sort them and use 2 pointers. The point was that we can solve it for n twice smaller. So, and I will not implement this, because implementation of this particular problem has nothing much to do with meet in the middle technique. Meet in the middle is just about saying solve the problem for half the input, solve the problem for the other half of the input, and then find a way to combine it. The way to combine it depends on the problem. It's like divide and conquer, just without the step of recursively halving further. Just like algorithm shooter says in the chat, actually, set of int is slow in C++. Better use vector plus sort. And the time complexity here will be, I believe, 2 to 20th power, n over 2, times logarithm of that if you want to sort or you want to put everything into a set, but logarithm of this is just n over 2, so we can say that this is the time complexity. Hi, Tanay. Moving on. Second problem. Given a sequence, count increasing subsequences of length 3. And there is a DP solution for this, but we will ignore it. This problem is solvable without meet in the middle, but let's not talk about that. Let's instead say that we don't know dynamic programming at all, and we want some other solution. Yeah, CSS is indeed very strict in terms of time limits. In particular, many problems you cannot solve in Python, sadly. But this stream today is mainly about talking about solutions rather than necessarily implementing them. Second problem. Given a sequence, find triples, increasing triples. For example, if the sequence is, let's say, 2, 5, 4, 1, 8, 9, 20, 15, then there are for sure many triples. One of them is 2, 4, 20. Something else, 5, 8, 20, and so on and so on. Brute force is n cubic. Iterate over all the triples and check them. There is dp quadratic solution. There is also dp n log n solution. But instead, I want to just speed this up to n squared because the constraints suggest that if n is up to 2000, n squared would be nice, and it will be enough. And how? Well, let's see if we can use meet in the middle. What was the requirement? If you can solve problem for twice smaller k. Well, if instead of 2000 they give me input of size 1000, that doesn't help much. It's similar value. Here it was a huge difference because from 40 we got down to 20 elements in every half, and 2 to 20 is small enough, and 2 to 40 is just huge. Halving 2000 doesn't really help. saying that it's 1000 cubic but for both halves doesn't help, and also you couldn't just do it like that because still you need to merge something, so that will not be faster. But there is another value in the statement. Another value is 3. And this 3 is our k, that if it's twice smaller, it would be much easier to solve the problem. I can rephrase the problem a little bit by saying that we count subsequences of length k, and I claim that with meet in the middle, we can focus on length k smaller, divided by 2. Instead of length 6, I would focus on length 3. Instead of length 3, I will focus on length 2 actually. I will always get from k to the ceiling of k over 2. This is what meet in the middle will give me. So the condition is satisfied, this one, because if k is twice smaller, so instead of 3 elements, I'm looking for 2 elements, so just pair of elements, I can do it in a squared. I can just iterate over all pairs of elements and check if they are increasing. Now, meet in the middle here is about looking in the middle. For 30 elements, the middle was 20 versus 20 elements. For 3 elements, the middle is the second of 3 elements. So the middle is second of 3 elements that you want to take in this problem. If there were 4 elements, then usually middle is something between second and third element. Now, what is the solution? And I think it might make sense for me to implement it as well. We are looking for pairs I, j, k, and I will focus on the middle, meaning j, and for it, independently, I will look for I and I will look for k. Let's talk about our example here. Let's talk about 8. 8 is a possible middle element of a triple. If 8 is the middle element, then the third element must be something greater than 8 to the right, which is 9, 15, or 20, 3 possibilities. Actually, 8 is a very bad example because everything to the left is smaller. Let's talk about 4 instead. If 4 is the middle element, then something greater than 4 on the right must be one of those, 8 through 20, 4 possibilities. And something smaller than 4 must be just 2. So ways for 4 to be middle is 1 times 4, which is number of smaller elements to the left times number of greater elements to the right. Those are numbers of ways to choose first element and third element. And if first versus third, those are independent, because just it matters that first is smaller than the second element, the middle one, and middle is smaller than the third one, then that's it. So quickly, the implementation is something like, for every j, being the middle out of 3 elements, I, j, k, I want to count smaller elements on the left and bigger elements on the right. For every I smaller than j, so on the left, if ai smaller than aj, then smaller plus plus. Similarly, iterate to the right of j plus 1. I will call it k because it will be easier to understand what's going on. K smaller than n, k plus plus. If that element is greater than aj, then bigger plus plus. And then answer plus equals smaller times bigger. For every element j, we independently counted smaller elements to the left and smaller to the right. Because those two for loops are not nested, you don't multiply time complexity. It's not n times n times n. No, because this for loop is not within this one. This time complexity of this code you're looking at is just n squared, not n cubic. We can find the answer by merge sort. I think it will be complicated with a merge sort, but I guess so. Merge sort is easy to find inversions. And you can simplify, by the way, those two steps using a segment tree, and then you will get n log n. If you know segment tree, then this can be done in logarithmic time. Similarly, this thing can be done in logarithmic time. But that's not the topic of the lesson today. So we can solve this second problem. And from this, a lesson is, if we are looking at triples, quadruples, anything like that, some small tuples, then focus on the middle element, iterate over that, and then count elements, count possibilities on the left and on the right of getting half the required tuple. And in that usually will improve the time complexity from O of, let's say, n to k power, the brute force, if you want k elements out of n. Instead of this, you have n to power k over 2, and you round it up. For example, here we had 3 elements. By focusing on middle element and just what happens on the left, we have n to k over 2 power. Why do we multiply smaller and bigger? Because if for a value like 8, if there are 4 possible elements on the left and 3 possible elements on the right, then there are, we see here 12 triples. If you have 4 ways to choose A, 3 ways to choose C, then possible tuples coming out of this is 4 times 3. We want increasing subsequence. So if 8, or if for example 4 is supposed to be the middle out of triple of increasing numbers, then before 4 we want something smaller, and after 4 we want something bigger. For example, a good triple was 5, 8, 20. 8 is the middle one, and indeed 8 is bigger than the left one, 5, and smaller than 20. Upload code on GitHub? I don't think that's in any way needed. This thing is not about meet in the middle, and CSS, actually that's not even CSS, but no, I don't see how it will be useful for you to copy paste that in any way. Similar, if you needed to count tuples of size 5 of increasing subsequences, subsequences of size 5 with increasing elements, you can focus on the middle element. It will be, such a tuple will be, let's call them indices I, j, k, l, m. Then I'm going to iterate over k and separately count possible pairs ij to the left such that they are smaller than k, and count pairs lm to the right such that they are greater than k, and we will multiply the number of ways to get ij by the number of ways to get lm. And instead of n to 5th power, you will get n to 3rd power, because for k you will iterate over ij. After that, you will iterate over lm. If you need a code, you can just rewind the video. Later everything is on YouTube. On Twitch, actually, it's also possible to rewind the stream. It's just more complicated. But if you really want it, well, here you go. This is code for increasing triples. Paste it in the chat now. Though I don't see how it's useful. Yeah, regarding the even k, we will see one example in the next problem. So moving on, it's now P3. P3 is a similar problem. Here, there is a very well-known problem to sum, where you need to find pair of elements summing up to S. Here we need to find 4 values summing up to the target sum. It's like increasing sequences, just more difficult. We already talked about one problem today where the sum of elements need to be exactly equal to x. And we used the complement method, where if the sum is 100 and you're looking at 20 already, you know that 80 is missing. We will use the same technique. I have a long sequence. Let's say that I can have n squared. I can iterate over 2 elements, and let's say that the target value x is equal to 100, and I'm looking here at 15 and 25. Then I know that what is missing is 60. So it would be nice to know if I can get 60 in some way. Can I later solve this problem? Not really, I have enough problems to go through. But Codeforces problems, they have editorials. So, if you're looking at two indices, let's call them ij, then you know what is missing. You want such two elements that a of k, I can just type it, it will be easier to see, a of k plus a of l should be equal to 60, because, well, 60 is what's missing if you already have 40 and you want 100. Now, this seems to be exactly like what we are doing here. We are iterating over pairs. We are finding here 40, then 60 is missing as the other pair. So there is an annoying solution in O of n squared, is find sums of all pairs. Sums of all pairs. And then create a list out of those. In this list there will be 40 and 60. You need to find a pair of values there that sums up to 100. But it is annoying because we don't want to repeat indices. Every pair comes from some two indices, and we actually want in this list of values like 40, I can reach 40 with those two indices. You need to now find a pair of elements coming from different indices. So for example, in this list, we might see that we can get 40 using index I equal to 4 and j equal to 6. Also, maybe we can get 60 using index I equal to 6 and j equal to 7. Those two cannot be combined, and that's very annoying, because if not for those, if not for checking if indices are the same, then is enough. This is a two-sum problem. We need to find a pair of values summing up to 100. So instead of doing that, there is a better approach. Instead, as we go through the sequence, if I'm looking now at this pair, ij, I want a structure that keeps information about this prefix so far and keeps all the possible pairs of elements there, basically the possible sum that I can get here. If there are elements 5, 7, 10, and so on, maybe 11, and so on, then I want a structure that already knows that I can get 12, I can get 15, I can get 17, and so on, few other values, all the pairs in this prefix. And now, when I'm looking at those two indices, I know what is missing for me, what two other values I want, and I will just look here for that missing value. Then I don't need to care about indices, assuming that my structure only keeps info about pairs up to here. So when I'm at ij, I want the structure to keep info about pairs up to I minus 1. So meet in the middle was here just about saying instead of quadruples of elements, I want to focus on pairs. And now, very related to this particular problem is how to exactly do it. Again, meet in the middle is not really like other techniques, like a segment tree, where it is some technique, you need to use it, and then you will just copy-paste the code. No, it's very different in every problem. If we store in a matrix, then we can leave out the corresponding row and column. Yeah, but how do we do it? If you have a long matrix, n by n, and in every cell you put some value, how do you quickly find in a matrix given value, except for this row and column? Yes, it is possible, but it's annoying. And I'm here proposing a solution without caring about indices that much. Okay, I will modify, I guess, the same thing. So here, first, this was the code for count increasing triples. And now there will be some, it's more like pseudocode for some problem. The sum of 4 values should be equal to x. Iterate over pair ij. And now we know that what is missing is this value, x minus ai minus aj. This is missing. if I want to get the sum equal to x. And I want to ask a structure, and this could be some dynamic structure. I want to, as I go with I to the right, it will get new elements. So let's say I have a set, possible pairs, I don't know, pairs. If pairs contains this element, then problem solved. Let's say we just need to check if this quadruple exists. So here I will print yes and return. There, exit from the full program. If this set includes this value, then good. And now this set should keep info about pairs up to I-1, which means that when I moves to the right by 1, so when this pointer moves here, I should also include pairs with this element. So when I have I, after I'm done with I, maybe I was equal to 5 a moment ago, and the pairs included everything up to 4, but now I will move to 6. And I want to know about all the pairs, including I equal to 5. Here, iterate over all the things up to I, and say that AZ plus AI is possible. Done. This is n squared times logarithm from a set, solution for some problem. If you want indices, you will need to change this set into a map. Let's talk about a small example. Maybe I will say what happens for this input. 3, 2, 5, 8, 1, 3, 2, 3. Initially the set is empty. Pairs is empty. Something happens for I equal to 0, we will compare it with j equal to 1, then we will compare it with j equal to 2, and so on. It will find nothing. But let's look at something more interesting. Let's say that I is already equal to here. I is there. I is at this position of 5. Then pairs contains a single value 5, which is 3 plus 2. Now I try to pair up I with this j, 8. 5 plus 8 is 13. What I'm missing is 2. The target sum is 15. I am looking at 5, 8. The sum is 13, so what is missing is 2. And I'm checking if in the pairs I have 2. No. Moving on. This pair, 6. Missing value is 9. Do we have 9 here? No. Next, we have this. 8. Missing is 7. Nope. And so on. Then I was a moment ago here. Now I will be there. This is new I. And those two pairs is something I'm including in the pairs set. So pairs will now be also with 7 and 8. And those are again all the pairs of values before I. And again, I'm looking at 8 plus 1, that's 9, missing is 6. 6 is here? No. 8 plus 3 is 11, missing is 4. Is 4 here? No. 8 plus 2, 10. And missing is 5. 5 is here? Yes. The end. So the solution we found was 8 plus 2 plus whatever pair here gave us a 5. In this case, it's this pair. But if you would need a map to restore the indices. A1, A2, I will comment on this. Paste. A1, A2 are independent from A3, A4. I wouldn't say independent, but you can independently look at them. And when combining, if you look at some pair A1, A2, you know what is missing, so you want just pair A3, A4, satisfying some one particular thing, requirement. Here, the requirement being their sum must be equal to something. Why are we not searching in the middle between I and j? Good question. No matter what quadruple is the answer, I will find it if the optimal quadruple is here. I will find it when being at this I and this j. Indeed, you might argue that if I is here, j is there, then I should also find the solution by saying those two are KL. But I'm saying, for my convenience, that ij are the last two indices, and I'm looking for the pair kl to the left. So, which means that in this code, my solution iterates over third and fourth element of a quadruple, because I'm looking to the left of I for the other pair. Can counting subsequence of size k, which are arithmetic progression? I guess, depending on the problem. But then the arithmetic step, the progression, it must be included. This solution related to dp? I don't know. If you want to call it dp, sure, it can be dp. I see why you're asking this, but I don't know the answer, whether we should do it or not. All right, first three problems done. Any questions right now? Next will be P4. You solve 1,000 problems and you're green? I don't know, maybe you're bad at math, or you're solving easy problems, or you're just retyping editorial. Is this useful for Division 2? Yes, in Division 2 rounds you can encounter meet in the middle problems. We solved P3 in quadratic time, times logarithm, so n squared log. Now time to move on. P4. Find a string with the standard polynomial hash equal to the target value x modulo billion 7. So what is hash? If you have string like Bob, okay, Bob, let's say Bob is fine, or let's say dog. Then polynomial hashing means that you convert every character into a value from 0 to 25, sometimes from 1 to 26, whatever really. Let's say from 1 to 26. Then this thing is really 0 to 25. This is 3. This is, I don't want to count. You can tell me what it is exactly. Let's say 12. I think later, so maybe 14. And G is D, E, F, G, 6. And I sum up those multiplied by every next power of 26, which is here. Depending on your indexing, it might be 3 times 14 times 26 plus 6 times 26 squared, which is equal to apparently 4,423. This is how hash of a string works. O is 15. All right, so we have 15. Thank you. Shouldn't it be 1, 2? Yeah, it should. It should. But if you also check the length, then it doesn't matter. If you wonder about it, like how other people do it, then just find any code forces problem where hashing is used and look at submissions in the top. You need to either use zero indexing and compare lengths when comparing the hash of two strings, or just use indexing starting from 1. Let's say here we use starting from 0 to say that we multiply by 26 exactly. Now, the problem isn't really about understanding hashing much, it's about applying meet in the middle here. And this time, there is no small value in the input. Well, the alphabet size is 26, so maybe it would, but is that really easier with alphabet 13? No. So this is not an easy problem. And for the first time, the sentence I told you first, this one, that you should apply meet in the middle. If some input value decreases twice, then you can solve it. This time the hack didn't work. So what do we do? This and one later problem will be a little bit of math. Can't we just convert x to base minus 25? I guess you're right. Didn't think about it. Okay, then I will cheat a little bit that only vowels allowed. I don't know. So indeed, converting x to base 26 or 25 will work. So to make it actually required to use what I want to use, we have update. Let me change statement update. Only you can use only vowels or only consonants, whatever you prefer. 2 to 13th can pass. It can, but I don't see a solution in this time complexity. Modulo billion 7. Yeah, modulo billion 7, but you can try to get x exactly. No. Here's what we will use. We can... There are two approaches to... There are two different solutions. Solution 1 is try random strings of fixed length. Let's say length is 10. And for each of them compute the hash. And then what we want is we want to add two strings. If we... How many times can we try a random string? Well, 1,000,000 times, maybe 100,000. And for each of them we compute the hash. Maybe one hash will be this, the other will be that, and so on. We compute all the hashes. And then we are looking for two strings such that the sum of their hashes, hash 1 plus hash 2, is equal to the target value x. This again becomes a two-sum problem. If the statement is exactly like here, then problem solved. What is, by the way, adding strings? Well, if you realize that this string has hash equal to 50, and this other string, I don't know, A, B, 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 has hash equal to 60, and you want to get 110, then you should just add those two strings in base 26. You will get B, B, D, B. I think this is the sum of those two. Then you will get 110. How to determine things length? Choose 10. This length should be small enough that it's fast, but big enough that you actually can get various random strings of this length. Like if you say just only get strings of length 3, you will not get enough strings. But here it will be better. And the fact that here we will be able to find two numbers with sum equal to x is some variation of birthday paradox. If you don't know what it is, look it up later and learn about it. Also, I have a video on YouTube using birthday paradox, but it's a difficult problem. It was top coder digit problem. If you let me check if we can find it. 4 distinct digits. This is a difficult birthday paradox problem. Here we are not really looking for birthday paradox, but something slightly different, but because values are random-ish, it will still work. And birthday paradox says that you need around square root of mod values, so that if you look at pairs of them, every value from 0 to modulo will be possible. Because modulo here is 1,000,000,007, it's enough here to try 30,000 or so, maybe let's say 50,000. Of course, slightly more will be nice, just to make sure. So 100,000. If you try 50,000 random strings, then the number of pairs they create is around, it's more than 1 billion, more than 2 billion. So should be enough. But in practice, we will just get more of them, like 250,000, just to be sure that we will get a pair satisfying the conditions. So the summary is, and it doesn't work for vowels, I agree, the other solution will. This is just alternative solution to exactly the statement from there. Let's say that the statement just says you cannot convert into base 26. The solution is generate 250,000 random strings of length 10, gather all those hashes, in the found list of hash values, find two numbers summing up to x, and modulo billion7, so they can like overflow billion7 as well, it's fine. And then add those two strings in base 26. Every corresponding position should be added. This way you will get something with sum of two hashes you found. It doesn't work if we have only vowels, but hence I will show you a second solution. This one is more something that I would call meet in the middle. Let's say that I want to get a string with length 10. If 10 doesn't work, then we will try 15. So I want a string of length 10, and I want to split it in half. And I will try all the possibilities, or again, random 100,000 possibilities of the left half. In particular, I will try here just AAAA, AAAE, and so on, all of them, or again 100,000 random them. For each of them, write down the hash value, and for the right half, also try random or all of them, but when computing hash value, remember that the indices here shouldn't be from 0 to 4, but instead from 5 to 9, because those are not first characters of our string. Those are first characters, and they will be multiplied by first 5 powers of 26. Those will be multiplied by next 5 powers of 26. And again, we list down hashes of this. Maybe even zeros are there. Maybe there is hash 0, hash 5, hash this, hash that. Then you have the other list coming from the right halves of the string. Something, oh, actually this is again 0. Then something big, and so on. And once again, sort those two lists and find something summing up to the target value. I know that we can consider the base 26. I will modify the block later to forbid that in some way. The vowels thing is some fix that I got quickly, I came up with, but it's stupid, I would say, because it also combats this first solution, which is perfectly fine. Right. Summary is that if you want to achieve every value from 0 to billion, then it's on average enough to get 30,000 random strings, or just in case 200,000, maybe 500,000. And then some combination of that, some pair of them, will sum up to the target value. Why do we need to sort the two lists to find pairs sum up to target? We can do it without sorting, for example with hash set, but that's I would say that's the best method to solve the two-sum problem. And by the way, two-sum also you can practice on CSCS. Is two values. If you want to solve problems from today, from the stream, then first you should solve sum of two values on CSCS. Can you read Persian? No, I cannot. Somebody told me that. Is this a viable solution? Yet we say we are not allowed to convert to 26 base. I know that it's a correct solution to this problem. I just want to show another solution. That's it. But the main lesson from here is that we can use birthday paradox. If we need to construct something hitting a particular value, often we will construct actually fewer elements and we will try to combine it to get the target element in it exactly. Questions? I will make sure later to update the blog. P5. You're given a graph and we want to count paths made of 5 nodes. I will need more drawings, so what was the here we go. You are given a graph. Count paths with 5 nodes. One such path is here. 1, 2, 3, 4, 5. Sorry, here. And the basic version of the problem can be solved with DP. Yeah, it's funny how Twitch is censoring messages here. I don't understand it. It finds something wrong with math formulas. I quote, then the message disappeared for me. But the Twitch asks me, should it allow this message because it seems suspicious, and it says that it can be racial or something. I mean, racist. And it's just a math formula. So we count paths of length 5, and I count length as the number of nodes. Basic version of that problem, if you look at the Codeforces blog, is that we also allow repetitions. So it's okay to count such a path. 1, 2, then 3, then 4, then 5. This problem is much easier if we can have repetitions. And then it's some DP on a graph, where DP of every node and how long path you have already. But I want to propose alternative solution that also can be applied if we don't allow repetitions. Taking adjacency matrix to the power of 5. But by non-diagonal elements, what you're doing is you're guaranteeing that the start and end are different. But how do you guarantee that other elements as you go are not different? Adjacency matrix here is an overkill. Like, it would make sense, matrix expo would have sense if the lengths of paths were big, like 1 billion. Then yeah, that's the solution. For small values like 5, DP is the solution. But again, unless you cannot have repetitions. The whole difficulty in this problem will be how to deal with repetitions. What is the brute force? The brute force is n to 5th power. You can iterate over first node, then over its neighbors, and so on. DP set of visited. Set of visited is exponential. I mean exponential. N to k power. Your DP is not polynomial. So this is slow brute force. And we have a value that is very low, and if we have a small value, and if it's twice smaller, we will be able to solve the problem in n cubic, because n is up to 300. So the goal is to speed this up to n to 3rd power. And for this, we iterate over the middle out of 5 nodes. Let's say that this is the middle. I will call it M. And what is the bit in the middle here? We consider paths going out of this node and continuing. And this is one example path. And we can combine it with some other path of length 2, like this one or this one. If you count paths with two edges going out of M, you know how many possible pairs there are of such paths. And the most basic version is this: if you can't have repetitions, is that if you just say that C is the number of such paths of length 2, in this case it would be 1, 2, 3, 4, 6, 7, and so on. It would be around 15, I believe. Then it will be, what, C squared? I think C squared, if you care about the order in this path, like what goes first, second, and so on. Every pair can be, you choose a green path to go before M and yellow to go after M. So you will just say answer plus equal C squared. Maybe it should be C choose 2. All right. Now, how do we count C? How do we count paths going out of M? Well, we just iterate over neighbors of M, and for each of them we iterate over their neighbors. Simple enough. Actually, even if you want to quickly iterate over neighbors of such a guy, just look at the degree of this one. So C is almost the sum of degrees of our neighbor, where B is in agency list of M. Sorry. This is C, the number of possible paths with two edges going out of M. Still, we are not interested much in this solution because it doesn't check for repetitions. Now, here's the real solution. Yeah, what if there is a cycle of length up to 4? Exactly, that's the issue. Here's the real solution. We focus on node M, at the middle one, and we find all paths of two edges going out of here. Each of them will be described by a pair of vertices. So maybe there is a pair 2, 5 going out of M, maybe there is a pair 4, 1, maybe there is a pair 4, 5, maybe there is also 5, 4, because maybe from M you can go to 4 and then 5, or the other way around. And so on. There is such long list. What is the size of this list? This is list of paths of two edges going out of M. And the number of such graph is not directed. Yeah, it's not directed, but doesn't matter. No matter if it's directed or not, the solution is the same. And there can be n squared elements or pairs. Because we find it by, for M, iterating over its neighbors and then over their neighbors. So clearly n squared. And now the task is count pairs of those pairs without repetitions in of size of the list. And this is, once again, like already we had in some other problems, something very specific to this problem. This is not meet in the middle anymore. Meet in the middle told us, or hinted, that we should focus on the middle element out of some tuple. Here it was third out of 5 nodes in a path, and now we have a new task. And this can be solved. Because the solution is something like this. For every element, let's say that there are... let's say that the size of the list is S. S is the size of the list. And then for every such pair, we should say answer plus equal S minus 1. S minus 1 is the number of all the elements except for this one. Minus frequency of 4 and frequency of 5. Let frequency of 4 be the number of pairs with at least one element equal to 4. Then those with at least one element equal to 5. But then if there is another pair with both 4 and 5, we subtracted it twice, so we need to add it back. This is frequency of pairs 4, 5 exactly. But then if you have that, I believe that you don't need this minus 1. For example, here, just looking at those 4 pairs, S is equal to 4. Then, what is frequency of 4? So among them, how many pairs have a 4? 1, 2, 3. Minus 3. How many of them have 5? 1, 2, 3. And how many of them have 4 and 5? 1, 2. This is equal to 0. This is very simple case of inclusion-exclusion principle. But very simple, or like 2-dimensional prefix sums. Though I think it's so basic that you can get this without knowing inclusion-exclusion in general. But what I described here anyway is just a solution to this problem. If those are maps, then that's size times logarithm, whatever. We don't care much about logarithms anyway. And problem solved. The whole solution is to iterate over node M, and then iterate over neighbors and their neighbors, which is n squared, and that's O of n cubic. We solved the problem of counting paths made of 5 distinct nodes. Simple paths made of 5 distinct nodes in a graph in time complexity n cubic. And actually it can be done in nm, because this list is limited just by edges in the input. I can even say this, because if 2, 5 is a possible pair, it means there is an edge between 2, 5. So this is O of m. So the whole thing can be solved in nm rather than n cubic, which might be lower if m is smaller. But what I want you to remember is if in a graph you count paths or choices of 5 nodes and they are in some order, focus on the middle one, so third out of 5. Questions? I will later, like in my previous lectures, I will later update this block with some written explanation and codes or pseudocodes. For CSES problems, so those two, obviously you can find solutions online. Maybe not obviously, but if you Google problem name CSES, you will find code. For P2, I already gave you code. For P4, well, you can experiment yourself. I think that will be most beneficial. For P5, I think it would be nice to have a judge. Maybe somebody will find it, then it will be posted in the comments. nm log n, yeah, I guess. Those logarithms are not really important, and almost always you can get rid of it by saying, oh, it's an ordered set, an ordered map. And if values are up to n, then you can sort it in linear time. If those are pairs of elements up to n, still can be solved in linear time. This log can be, you can get rid of it. Were you inspired by my blog? Better solution to hard graph problem. Oh, I see that in this blog you're mentioning there is my answer. Oh, so we have a problem like this. Find a path of length 9. That's a nice related problem. I guess I will put the link to this one in the comments. So thank you for a link. I didn't remember this one, but for a long time already I was aware of such a trick. I guess I saw it 5-10 years ago in some programming camp in some problem. I recall techniques, but I don't really have good memory to find a particular problem. For a long time already I used this example of something of length 5 to use in meet in the middle. Watch my videos during college. Don't even have time anymore. Well, that's life. I hope I'm happy you like the content. The log factors are not important, and don't use unordered sets and maps. Their pessimistic time complexity is bad. So I just use set and map. I don't use unordered versions. And logarithms very rarely hurt in competitive programming. P5 done. Next is P6 and P7. P6 is from, I guess, Iranian Olympiad. But we will not talk about much details here. You can absolve though. This is why you have a link. Again, not again, but we need to find two subsequences with equal sums modulo m. And for this, I will just tell you that we already solved a very similar problem today, and that was P4. So P6 is about birthday paradox. If you try random sequences, after 30,000 tries on average, you will find two with equal sum, and that's it. Also, you shouldn't try sequences of length n because that will take a lot of time. Just focus on the first 30 elements or first 20 elements, however many you need to really get random sequences and not have a lot of repetitions, because that's wasted time. So P6 is very similar to P4. Treat it as homework to get the details here and to implement it. I think then it's okay that we don't have a link for online judge in P4 because you can just solve P6. And next, P7. Number clicker. Before P7, let me say let's say 7 easy. I couldn't come up with proper modification of this problem, but let's say that we have a starting string, s1 is equal to something. We have the target string, and we need to find sequence of moves that leads from one string to the other, and there are some rules. Maybe always one character you can change by one, but also no two consecutive characters are equal. There are some rules. So in one move, change one character by one. For example, from B to C or from B to A, with some extra rules. And rules can be anything. They can even say the hash of the string must be even. Something. Actually, that would be a stupid rule, I think, but whatever. Would random shuffle be necessary? No, because I guess if in P6, if the first elements are just powers of 2, then we lose. I didn't think about details. Good question, Osmosian. So in P6, maybe if numbers are not guaranteed to be random, maybe we need to take like 50 random elements. I would just take 50 random elements to be sure, but first 50 elements without random shuffle should work as well, because we are guaranteed to hit something there. I don't know. Good question though. I wasn't prepared to talk much about this problem. All right, back to P7. If there is this problem of moving from one string to the other, and if we know that the number of steps is limited, maybe we know the following. We make, I don't know, let's say 20 steps in total, and in each move there are maybe 8 possible moves. But again, I didn't know how to phrase the statement exactly, so I couldn't say that this is the problem. But it shows the solution. The brute force for those constraints is 8 to 20th power, which is too much. We don't want that. But if we divide something by 2, it will be fast enough. if we divide 20 by 2. It would be nice to just focus on 10 steps, because 8 to 10th power, I guess it's still not enough. Okay, I'm cheating. 6, 5. This is fast enough, let's say. If it's enough to just consider half of the path from starting string to the final string, then we're good, because we can just consider all those possible paths. And the solution is, and this is, I guess, the most literal meet in the middle thing, like we literally will traverse and meet in the middle, is the following. Start from S1, traverse some path of length up to 10, simultaneously or later start from S2 and go the last 10 steps and try to meet. If path length should be k, consider k over 2 steps from start, consider k over 2 steps from the end, try to make them meet. Okay. So find all the paths from the start, remember where you can get, do the same from the end, remember when they can get, and in those two lists you need to find the same node. This is a solution to this problem for which I didn't set exact constraints and exact rules. Obviously, we need to be able to apply the moves backwards as well. From S2 we will go to the other way. And this is a reasonable speedup for various graph problems if we don't care really about the time complexity, but we care just about real running time, where if you have a map, some kind of grid or a maze, and you want to find the shortest path from one point to the other, then instead of just doing BFS from the start, you can run simultaneously BFS from the start and BFS from the end, so they would kind of spread here evenly, and you hope that they will meet fast. If the distance is small, then they will meet fast. And here they would meet, I guess, there. So always we find with blue BFS one next layer, so everything at next distance increased by 1 from the start, and yellow BFS again we consider one layer. In real life this is often useful. If I was to implement a video game where there is a grid and a unit needs to move from the current position to some new position, I would either implement the A* algorithm, which works very well, or I would do it with simultaneous BFS from the start and the end. Will there be a replay of the stream? Yes. In particular, all these old streams are on YouTube, but also on Twitch. See the YouTube 2 channel, Aricta 2 YouTube channel. Yeah, the time complexity is the same for general graph, just in real life, and for such grids, often it is better because you will not traverse the full grid. Treat this more like an intuition rather than better time complexity. The actual runtime would speed up in the... So don't use it in competitive programming just because you hope so. There will be malicious tests. But in real life, in video games, it's different. Multi-source BFS? Kind of. You can think about it as multi-source BFS, but then you need to be careful there for every node to remember what was the source node. So in P7, if we need to get from one string to the other, always there is small number of moves possible, and the total path will be again small in length. Then make some moves from the start, make some moves from the end, and make them meet. Finally, real problem P7, number clicker. We have some modulo given. Let's say that P is equal to 13. And here's what we can do. If we start from number 10, then we can change it to 9 or we can change it to 11, so increase or decrease by 1, or we can change it to its modular inverse, which is a randomish number. It will be equal to something. I don't know really what it is. 26, 39, so a 4. I think 4 is modular inverse of 10, modulo 13. And then again, from 9 you can get 8 or 10 or the inverse of 9. From this, 10, 12 or inverse of 11. From this, 3 or 5 or inverse of 4. The statement is here. We need to, given p up to 1,000,000,007 or so, we need to find a path between A and B. This is the combination of some previous problems. By the way, if you want a challenge, you can stop watching now and try to, using the knowledge you got so far, just solve this problem. And by the way, this is how I recommend watching the recordings of streams later. Once you get this lecture already recorded, then don't watch it just in an hour and a half, but stop, think about the solution, then continue. After k steps, you will get around 3k numbers. 3 to k, not really, because of this -1 versus +1. Right? If you keep from this, you get 8 or 10, or this or 12. So 10 will be repeated a lot, and again from 10 we will get 4. There are a lot of repetitions, but I think we should expect at least 2 to k power numbers. We will have a lot of numbers. The solution is combination of birthday paradox and this going from the start and from the end. So solution to P7 is get many random paths of length 100 from the start and get many random paths of length 100 from B and make them meet. Instead of really thinking about this 2 to k power or 3 to k power, anything like that, we just do what we can in time. So the solution indeed involves a little bit of birthday paradox. Not really that. Birthday paradox has some assumptions about this randomization. Here we have some process starting from A, starting from B, and they are very different from each other. But if we assume that the inverses behave randomly, they are random-ish, at least then this should be fine. That it's not that starting from A in 100 moves we will get only even numbers, and from B we will only get odd numbers for some reason. That shouldn't be the case. Also, I would for safety say of length up to 100. So if you in 99 steps got somewhere, also remember that. And by many paths I mean however many you can get. 100,000? If you can get 100,000 in time, just get 100,000 and hope that it works. It should for sure be greater than square root of 1,000,007,000. Yes, those solutions are probabilistic. But whenever you have randomized or probabilistic solution, what you want to happen is that you have the 99.99% probability of being correct. That's always the case with hashing and with anything randomized. So if birthday paradox is able to explain how if we get enough elements, then it's almost certain that there is a repetition, then we're good. We solved many problems using birthday paradox. I don't want to today talk about birthday paradox more, but I told you that there is that video, my video on YouTube about top coder digit problem. And there are for sure articles online. Any questions about P7? The codes and pseudocodes or links to them will be here. Obviously for CSS and Codeforces problems, you can just look up solution yourself. Verify birthday paradox, but that would require, rather than your one question, everybody would need to just say their birthday. For sure, birthday paradox doesn't work like one person just saying their birthday. and then everybody saying no, 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 no. That's exactly not what birthday paradox is. And I guess people aren't, you won't get here a lot of people keen to answer, but I think with 30 people, you have like 99% that there is a repetition. Even more if there's some correlation, meaning that in some months more people are born, which might be the case. Just because of like planning for the summer or something like that. All right. Yep, exactly. Probability that you are that person. So exactly somebody has 6th of April is here 1/3 if we have 100 viewers out of 365 days. Oh, I had randomized lecture. Oh, here you go. I shouldn't now talk about birthday paradox because I have a lecture on that. Good. Then for birthday paradox, randomized and hashing, go watch that. Birthday paradox and randomized lecture. Thank you, Jero, for the link. I actually forgot about it. That was meet in the middle. Summary is that something needs to be small in the statement, and if it's twice smaller, you can solve the problem. But also we saw this category of problems not really being meet in the middle, like those two, but related to birthday paradox. If we want to, or we want to hit a value up to, for example, 1 billion, and then we generate much more than 30,000 random elements. So I'm sure some people will argue that this is not meet in the middle, but well, sue me. Thank you everybody for watching, for asking questions, and see you tomorrow, because if you look at my calendar of streams, which is here, you will see that tomorrow morning, just like 20 hours from now, I will watch live the ICPC dress rehearsal, just to chill a little bit and complain how ICPC is stupid and they force everybody to use free computers. They forbid them from using one computer, which is, I think, very, very stupid. So hang out with me there, and I'll see you next week for AdCoder hard stream, maybe Wednesday or Thursday, the problems of the week on Saturday, and again some topic stream on Sunday. That's the plan for next week. Bye bye.